Welcome back. In this video, we're going to talk about an introduction to graphing planes and surfaces in R3. Very exciting because this sets the foundation for the calculus that we're going to get into. Remember that when graphing planes and surfaces in R3, we're really talking about equations with three variables. To get our head around how this works, we're going to go back to our study of equations and the types of equations that define surfaces and curves. For an introduction to this, you can see the video in lesson 2.4 about graphing in Mathematica. Recall in that video we spoke about two categories of equation types that define graphs and curves in R2 and R3. So one type of equation we called explicit function equations. And in explicit functions equations, we write an equation where the unique output variable or variables are isolated on one side of the equal sign, and these output variables are written as a function of the input variables. We call such an equation an explicit function representation of the output in terms of the input. Explicit because literally the output is given in terms of the input. These function representations, when we graph them, they will pass the vertical line test. This is what we know and love from our previous lives before we were reincarnated in this bizarro world that we're in now. All right. So an example of an explicit function representation in R2, the general form of such a function, is given as y equals f of x, where this is some expression explicitly in terms of x. In this general form, we call the output variable, which is isolated on the left-hand side, y. We think of x as our input variable, and then we see that y is written explicitly as a function of x. When we think about graphing such a function, we actually suppressed this detail in Math 1A and B, but really that function is a collection of ordered pairs. It's all the ordered pairs x comma y, where the second coordinate of that ordered pair is given by f evaluated at x, and then we have to check that x is in the domain. When we graph these, we get some collection of ordered pairs in R2 that passes the vertical line test. Since Math 1C is a generalization of Math 1A and B, we're going to see that explicit function representations also exist in R3. The general form of an explicit function for a surface in R3, not a curve. Curves are in R2 or parameterized in R3. But we also have surfaces in R3, and the explicit function representation is z, the output variable, isolated on the left-hand side, given as an explicit function, lowercase f of x, y, where x and y are our input variables. In this case, our output is written explicitly as a function of our two inputs. Again, this representation suppresses details. One of the major ideas that we're playing with here is that when we write a function like this, we're really looking at a set of ordered triplets. This set of ordered triplets we might call lowercase f. It's a bit of abusive notation since this is a set and this thing right here is a function, but they happen to correspond with the same ordered triplet points. So here we have x comma y comma z, and then the condition on these ordered triplets is that the output variable z is given by evaluating the equation f at inputs x and y, and then of course x and y should be in the domain. So we shouldn't evaluate this thing anywhere where it doesn't make any sense. When we graph such a function on the x, y, z axis, each unique input pair corresponds to one unique output. That's what we call a function. And these graphs pass the vertical line test. So if you passed a vertical line through any point on these surfaces, it would only touch once. That gets us our first category, which we call explicit function equations. We'll look at an example in the next video of explicit function equations for lines. We had a second category of equations, which we called implicit relation equations. And when we talked about implicit relation equations, we said that these equations represent situations where it is hard to isolate the dependent variable in terms of independent variables. In particular, implicit relation equations are equations in which the dependent variable is not isolated on one side of the equation. The graph of the points that satisfy such an equation do not necessarily pass the vertical line test. This is a less stringent form because we don't have to have the output in terms of the input. We can just have a single equation where they're written together but not isolated. Of course, implicit relation equations exist both in R2 and R3, and we will adopt a general form. This is going to come back big time when we start talking about the tangent planes and then tangent lines at a point. So the general form of an implicit relation for a curve in R2 is given by capital F of x comma y equals 0. So in this general form, we see that on the left-hand side, we have an expression in two variables where it's hard to isolate the dependent variable y in terms of x. The equal sign, where on the left-hand side we have two variables, so this thing represents a curve in R2, and then the right-hand side in the general form we set equal to 0. This description, of course, corresponds to a subset, capital F of R2, where capital F is not the name of the expression on the left-hand side. Instead, it's a set of all ordered pairs x comma y that satisfy this equation. So it's all x comma y that make this equation true. When we graph this, this will correspond with a curve. Of course, not only do we do this in R2, but we also do it in R3. Implicit relation equations in R3, instead of having two input variables in the general form, we have three input variables, and these correspond to a surface. So here we have capital F of x comma y comma z. This equal sign has to do with three variables, so this describes a surface, and in the general form we expect the right-hand side to be 0. When we write an expression in terms of these three variables, the implicit form indicates that it is probably hard to isolate the output variable z in terms of the input variable x and y. And by hard, we mean that it might take a lot of work, or it might be impossible, or if we do isolate z in terms of x and y, we actually will lose information by doing so. Once we have this general form of an implicit relation, we can look at the corresponding subset in R3. Capital F, we'll give it the same name as this expression, and in this case it's going to be the set of all ordered triplets x comma y comma z that make this equation true. The graphs of these corresponds with surfaces that don't necessarily pass the vertical line test, which is what we talked about. One last thing that I'm going to say, when we look at implicit relations in R3, we will often use the contour plot 3D command in Mathematica. Of course, implicit relations in R2 are not in 3D, so this is just contour plot command. Anytime we have an explicit function equation, instead of using contour plot, we'll use the plot command. So if we have a explicit function in R3, we'll use plot 3D command. And then an explicit function in R2, we'll use the plot command. So these are kind of the distinctions. As we go to graph these in Mathematica, we can categorize which command we should use based on the equation type that we're looking at. In the next video, we'll get our head around how to use this to graph lines, both implicitly and explicitly. Ready? Here we go.